Hi, welcome to the WiDS Mysuru workshop. In today's workshop, we will be talking about what is machine learning. And to give a deep dive, we will also be understanding about machine learning in the context of solving business problems. To explain this, I'll be using the Car Dekho dataset. It is a very famous dataset and it is publicly available on different sites. So, for example, you take it from Kaggle, or even if you just Google it. At the same time, I'll be sharing the link of the dataset and I'll be also um, uploading the dataset below. You can download the dataset from the link below. Um, okay, we will also be understanding what is EDA, exploring the data to get the different perspectives in terms of descriptive analysis, the different techniques that one needs to follow when we are conducting an EDA to any form of data, and why EDA is important. After the EDA, we will be understanding regression models. That means using different regression model techniques to predict the y variable. And in this case, my y variable will be the selling price of the car, which is also in other terms called as the target variable, using the independent features in the dataset. All right, so let's quickly first understand what is machine learning. Now, as we all know, and we've been reading a lot about it, if we just even research or Google it, we come to a very concluding definition that it is a branch of artificial intelligence and computer science which focuses on the use of data and algorithms in such a way to imitate the ways humans learn and then gradually improve on its accuracy. So, machine learning being a subfield of artificial intelligence, in simpler terms, would mean give the computers the ability to learn explicitly, sorry, explicitly without being programmed. So, machine learning, if we think about the examples around, um, is everywhere. For example, the chatbots that we interact with while we are surfing on a website, or the predictive text, different language translation apps that we use in our daily lives. If Netflix is recommending a movie to us, or the social media feeds in, for example, Instagram or LinkedIn, and all these things, they do have machine learning algorithms behind their operations or behind their functioning. Machine learning also powers autonomous vehicles, and machine learning is one of the very important technique that is now being used in medical sciences, especially to diagnose medical conditions based on, say, images, MRI scans, and different reports to detect medical conditions. And then it is very helpful for them to diagnose and further decide on the medical treatment that should be given. So when companies are talking about deploying artificial intelligence programs, so they are most likely using machine learning, and machine learning and artificial intelligence, in a lot terms, they are used interchangeably or sometimes even ambiguously. Now, machine learning is further segmented into three major branches, that is unsupervised learning, supervised learning, and reinforcement learning. So, unsupervised learning is something to do when we are dealing with data that does not have a labeled observation, or we could say it is an unlabeled data, or there is no final goal to be predicted in that set of row column um, data set. Simple examples could be um, companies when they are doing customer profiling. That means when they are creating groups or clusters of different customers behave depending on their customer behaviors or their buying patterns or their shopping patterns, then that is called as supervised learning. And as the diagram over here depicts it very nicely, that means creating clear clusters of similarities or which have similar associations. Moving on to supervised learning, which means again predicting, um, say, a final goal. That means for companies, if they want to predict the price of a particular product basis certain features, then predicting that price is a supervised learning. That means there is a goal or there is a target to be predicted or forecasted basis certain history or certain features in a tabular data format. While reinforcement learning is a set of is a subfield of machine learning, which is based on feedback. Uh, in other words, that means the algorithm is developed in such a way that it keeps improving basis on the feedback that it receives. And when I talk about feedback, it would be the different data set examples that the algorithm receives. All right, so now we'll be talking more about supervised learning in this session, and because regression models are a part of supervised learning. But before going to that, we will understand what EDA is. So for this session purposes, I am actually using a Jupyter notebook. And in this Jupyter notebook, um, I have also imported certain packages and which are very important to run through the different techniques and the different functions that we need to conduct the entire exercise. So in this Jupyter notebook, or if I say while doing it using Python, there are certain packages like pandas and numpy, which we will be using to explore the data and to understand the numerical and the categorical data. Data, basically doing a lot of data massaging, data wrangling. Visualization libraries such as Seaborn, Matplotlib, which I'll be using majorly in this session. SciPy.stats, that is package which is very commonly used for doing statistical analysis and the statistical tests. And here I'll be using it for running the QQ plots or the quantile plots. Ignore warnings just to keep it really clean in terms of the code and the output that has been generated. So just to not have a lot of warnings and a lot of messages. So I am running importing this library. And finally is machine learning libraries, which and the most common and the most known one is scikit-learn or sklearn, where I'm importing multiple functions. So for example, train test split is will be used to make a split of the entire data set into the train and test sets. Then a couple of data transformation functions like one hot encoder, column transformer, basically to convert them into a language that the algorithm understands. Standard scalar is a technique for, again, transforming the numerical data on a similar scale, just to um, remove the bias of the magnitude of numbers, and it's a pre-processing technique. Then we will be covering different models like SVR, decision tree regressor, random forest, linear regression, lasso ridge, elastic net. So these are different kind of models that we will be running through in this session. And lastly, important metrics which are required to assess how good the regression model has been performing, majorly looking into R square, mean absolute error, and root mean squared error. Okay, now the first and the foremost step to conduct any machine learning algorithm or technique is to import the data. So here from Pandas, I'm reading this CSV file that is just by using this function called read underscore CSV. I am calling this data set in my Jupyter notebook. And then with data.head, I am seeing the top 5 observations. By default, with data.head, you will be getting as your top 5 observations of the data set. So to explore further, what are the different features here in this data set? Here we can see that there are 2 unnamed columns. So they look as unwanted columns, and we can definitely remove them because they are not going to be used anywhere in our analysis further. And then understanding the other column names and the information that they carry. So there is the car name, brand, model, as the name suggests. That means it could be the brand, it is the brand of the car, the model of the car, vehicle age, which means the count of the years since when the car was bought. Kilometers driven is how many kilometers the car has been driven. What is the seller type? That means who is selling this car, whether it is an individual, whether it is some dealers. What are the fuel types? If it's a petrol car, it's a diesel car. Transmission type, that means if it is a manual car or an automatic transmission. The mileage of the car, engine of the car, max power, seats, how many seats are there in this particular model of the car, and finally is the selling price. So selling price over here becomes my target variable, and the other 11 features, they become the X variables when we will be running the regression model. Okay, so to understand what are the most important steps that is required to run regression models? Firstly, an EDA or feature engineering is required. Now, EDA is, in simple terms, means to just explore the data or the raw data as is, to just understand and gain insights from what the raw data has to say. So it's just simple as just trying to gain or understand the story of the data that it tells you. How do you So when we need to understand a story, so we also need to understand what are the characters of the story. So the characters, what's the plot of the story, if there is continuity in the story, or if there are breaks in the story, if there is something which is unusual in a story, and if there are some more terms, or there are some cases, or there are some plots which do have overlapping of the story. So, like how we build on a story, similarly, EDA is more exploring the data, and the steps that one needs to conduct while doing this EDA is doing a descriptive analysis, which means getting the statistical data, or the statistical, doing a more in-depth um, um, analysis of the numerical or the categorical variables that tabular data should be having. And when I'm saying about numerical data analysis, it would mean to quantify in a way that it can be explainable. The numbers can be explainable in terms of the mean, mode, median, percentiles, um, majorly. Then the adjustment of variable types, like similar to the story, understanding the characters, here variable types would mean understanding the columns or the features that one has in that tabular format. Um, and then detecting missing data. That means in a particular column, if there is missing data, that means there is no data, or there is just a chance of not or not having data, or the data is not necessary in that particular column, and that is why there is no data. So to understand that also, that is doing a detection and treatment of missing data. Identification of an atypical data, that means if there is something which is standing out from the usual uh, data points, which um, in machine learning terms would, or in statistical terms would mean detecting outliers, detecting unusual patterns. And finally is the correlation of variables. If two categorical variables are giving you the same kind of information, so maybe we can drop one categorical and use the other one. Or if two numerical variables are giving the same kind of information, so we can drop that. Because while we are building up regression models, we do face challenges and issues of biasness, or overfitting and underfitting problems. All right. So the next thing after conducting the EDA is to understand the different kind of regression models. So there are several types of regressions. And the most commonly, or the most known regression methods are linear regression. Now, linear regression has simple linear regression. That means there is just one feature basis which we will predict the y variable or the target variable, or or multiple features are going to be used to predict the target variable. So that is linear regression. There is polynomial regression, support vector regression, the regression method where we want to very categorically classify um, between apples and oranges. Then decision tree regression, more of categorical features are there, and basis that we want to predict a numerical y variable. Random forest is again an extension to decision trees. Ridge and lasso regression, these are techniques for dealing with biases, overfitting and underfitting, because if there are many features in the data and they are further explaining or giving in the same kind of information, so we might want to look into ridge or lasso regression. And lastly, logistic regression, which is a special case of the regression models, because here one predicts the binary classes rather than predicting an actual value. So a very simple example would be temperatures. So if you would want to predict what is the exact temperature tomorrow in Celsius or Fahrenheit, then that is a regression problem, because we are trying to predict the exact number. Whereas if we want to predict whether it is going to be hot or cold tomorrow, then that is a binary class problem, because we are predicting the likelihood or the chance of a particular event happening versus the likelihood or chance of the event not happening. Okay, so for this session, we will be talking about these models, that is namely as linear regression model, decision tree regression model, elastic net regression, and an SVM model. We'll run through the codes and see what is our output, and then in terms of understanding some metrics like the R square and RMSC, and understand if they actually mean something, and see if then we can do a little bit of hyperparameter tuning and improve the accuracy of the models. So first, we understand the data. So to understand the data, Pandas has got really beautiful inbuilt functions like functions. So .info, describe, shape, columns. They are used to understand the structure, the type of variables, the statistical summary of the data. Duplicated drop duplicates are used to look for duplicate values and drop the duplicate values. And also dot drop over here is used to drop the unwanted columns or rows in the data set. So like over here, data columns is to get the names of all the columns that are there in the data set. So if I print the head over here, I'm getting the top 5 observations. And if I'm printing the total rows in the data and total columns in the data, so this information, so there are a total of 15,411 rows, that means observations, and 15 columns or features in the data set. So the first activity over here is removing the unwanted columns. So as previously we saw that unnamed 0 and unnamed 0.1, they were just unwanted columns. So I have just dropped them over here. Axis equals to 1 or axis equals to 0 is basis if you want to drop a column or if you want to drop a row. In place equals to true, that means if you tag it as true, that means you are just removing it from the entire data set, and going forwards these 2 columns will not be there in the data. So now if I just again look at the data dot shape after doing this drop code, then I'm left with 15,411 rows and 13 columns, right? So that means these 2 columns are removed. Next, to get an understanding about the features of the data, so data.info. Now here To understand the summary, what information that we have is, we've got the total number of columns, the column names, the data types of these columns. So object would mean that it is a categorical column. Int 64, float 64 would mean these are numerical columns, and float 64 would also further mean that there are decimal values over here, whereas int 64 will have integer values. So here, if you see non-null, that means, and all these columns have 15,411 values, which means that there are no missing values, at least in this data set, right? So, and here it's a small description about how many floats, integers, and objects. Moving further, descriptive statistics. So to find out the descriptive statistics, data.describe is used. Now, when I run data.describe, so all the numerical features will, the output that will be thrown will be the numerical features over here. And data.describe by default will give you information regarding the count of these numerical features. That means how many columns are filled with numbers, the mean, standard deviation, min, 25 percentile value, 50th percentile value, 75th percentile value, and the max value. So this gives you a good numerical description about the data. So if you want to understand how this means, is that in vehicle age column, there are 15,411 data points, where the mean vehicle age is 6 years and a standard deviation of 3 years. The minimum vehicle age is 0, that means very recent. 25th percentile, that means 25% of the data values are less or equal to 4 years. 50th percentile, 50th percentile value is 6, that means 50% of the data is less or equal to 6 years of vehicle age, and 75th percentile or 75% of the data has or 75% of the car's vehicle age is less or equal to 8 years. Now here there is a vehicle which has got a max year of 29 years. That means this looks a very vintage car, or a car which is there for a long period. So we'll need to explore in further and understand which car is it, and does it actually mean 29 years, or it could be a typing error. Okay, but yes, this looks like a outlier and it stands out. Likewise, we need to interpret the other numerical columns also. So for selling price, we see that 50% of the values or the selling price, sales price of the cars that we have in this data set are around 550K. Okay. Now, and then there is a max value also, okay, which looks really huge compared to the 50th percentile value, where versus 75th percentile or 75% of the selling price of the other cars. So if you just do dot describe, then you just get the numerical summary. But if you want the summary of all the categorical and the continuous or the numerical data, then we can add another parameter to here, which is inside describe, is include equals to all. And then it will give you the details of all the variables. So for example, if we take the car name, there are 121 unique car names, and the name which has been stood out most times is Hyundai i20. Okay, and Hyundai i20, and the frequency of the most stood out name is some 906 times for the car name. So that's how we interpret the categorical data. And if you see the numerical columns, they have the similar information as in the as above when we were just doing dot describe. Okay. Now, some important insights that we can look over here is that max kilometers driven and the 75th percentile values over here, they indicate outliers. So kilometers driven over here, the 75th percentile or 70% of the data or the cars have kilometers driven less or equal to 70,000 kilometers, but then there is some um, car which has been driven way more than most other cars. So that means there could be a possibility that there is an extra zero out there, or definitely this car might have been used for so many kilometers. Selling price, also max selling price over here is somewhere around 39.5 million, whereas mean price of the cars tend to be around 770K, and median is around 550K. So we need to explore more in the selling price or the sales price also. Outliers, you can check in, this definitely stands out. The outliers stand out looking at the max values. Skewness, kurtosis, these are again another ways to check for outliers or something which is standing out for the numerical features. So we can see that kilometers driven and selling price, they are positively skewed because they've got quite a high value. And the same thing is being thrown out when we just run this data.cut, which is to look for kurtosis. Kilometers driven has got a huge kurtosis value, and selling price has also got a positive value. So the interpretation over here works is that it indicates about outliers present in the data and the data distribution. Kilometer driven and selling price, they're highly positively skewed. Now, the next step is in this data to understand there are duplicates, there are missing values or none values. So I've run this code over here, data.duplicated.sum, to see how many duplicated rows are there. So before removing the duplicates, there were 167 duplicated rows. But after removing the duplicates, there are 0 duplicates now. This missing no is again another package to look in for missing data. So from missing no, I am just importing metrics function. And if I just run this metrics function across my data, I see that there are no missing values. That means it's just clean. Likewise, I am also getting the same information by running this piece of code, which is data.isNull.sum. So everything is 0. That means there are no missing values out there. Okay, so the missing value check is done. Removing duplicates is done. Looking at the categorical features to understand how many levels are there in each of the categorical features. So car name, brand, model, seller type, fuel type, transmission, these are categorical features. And the other ones are numerical features. I've just written a small code over here, which is a comprehension to just segregate them into separate variables. So categorical features and numerical features just separate variables, and making a list out of what are categorical and what are numerical, basis their data types. So if it is an object data type, then it will be as a categorical feature, but if it is not an object data type, then it will automatically come under the numerical features variable. For the categorical features, I'm listing out how many individual categories are there. So car name has 121 different categories. Brand name has 32. Model feature has 120. Seller type feature has 3. Fuel type has 5, and transmission type has 2. So if you just look about transmission type, intuitively thinking manual and automatic cars are there, and that is why it is giving you as 2 number. Now, understanding so visualization, if you have graphs and plots around, that's a better way to visualize and get a hang of the data than just looking at numbers. So to explore that, these visualization plots, I'm going to run some box plots, histograms, and scatter plots and pair plots to see what the different variables are, and if my understanding is same just from looking at the data.describe, which we saw earlier here. That means this part. Okay. Now, so here, this first plot over here is looking at selling price. I'm looking at the box plot, and seeing, we can see it is very clearly identified that there are a lot of outliers. And the data is very, very skewed for selling price itself. So that's what this box plot depicts. Next is density plots, just to see how the numerical distribution has been done. So mileage is evenly, so there is a bell-shaped curve over here, so mileage is distributed evenly. Whereas if you see if you see selling price, there is quite skewed. Max power is also skewed. Engine is also having a skewness. Right, so this is how we can look from the box plots. Vehicle age also, though there is a bell curve over here, but then there are outliers also which has been present, and which we also saw in the description data.describe, that there was a vehicle which had an age of 29 years. Now I'm running through this plot, is looking at the categorical variables, seeing how they look like, just to get a pictorial representation of the categories. So we know that car name had a lot of different categories, that means 121, and that is why this looks very overlapped. Brand names, these are some brand names, and this Maruti, Hyundai over here, they turn out to be some of the most well-known brands in this data set. Models, again, too cluttered because there are a lot of different models here. Transmission type, there are 2 transmission types, and that's what we figured out initially also, manual and automatic. Fuel type, 5 of them. Petrol, there are petrol cars, diesel, CNG, LPG, and electric cars. So definitely petrol and diesel, they take the majority of the chunk of this data set. Individual, dealer, and trust mark dealer are the seller types. Looks like maximum cars are coming in from dealers, and the next one is individual people. So there are dealers who sell cars more on the Car Dekho website than individuals. Now, to just understand what are the top 10 categories in each of these feature, we can run this set of code where we saw that Hyundai had the maximum percentage was taken by Hyundai i20, and then there was Maruti Swift Desire, Likewise, if I have to see in terms of the brand, Maruti and Hyundai, they are taking the maximum portions. I-20, Swift Desire again. Here the model names are also given. Dealers, like we also saw in the graphical representation, petrol, diesel. They so 49% are petrol and 48% are diesel cars over here. Electric and LPG are really very, very small, hardly any one of them. Manual, maximum of them are manual cars, and just 20% of them are automatic cars in this data set. Looking at the top 10 brands with respect to sales. So, yeah, if we see in respect to sales, that means in respect to their selling price. Then, or in respect, sorry, not the selling price, but in respect to the count of these sales, right? From this plot, we are looking at the count of the sales. Then we can see that Maruti has got the maximum count in terms of sales, and then Hyundai, and then Honda and Mahindra. But the bottom 10 brands with respect to sales, that means those cars which were the least sold, we can see the bottom 10 brands, they were Nissan, Lexus, Isuzu. So, right, so these are very rare names, Mercedes, Ferrari. So obviously you can see that these are those expensive cars ranges, and that is why they could be those bottom 10 brands in respect of the count of the sales that are happening. The top 10 brand with respect to their costliest car, of course, in terms of the price over here. So it is Ferrari, then there is Rolls-Royce, Bentley. So this graph gives you that representation. What are the top 10 cars that are there? Kilometers driven with respect to selling price. Now this is more, it is a scatter plot where we're trying to see different, there are three parameters. One is the price, the kilometers driven, and we are also including the seller type. So the blue dots are the cars which are being sold by individuals. Green dots are the ones which are sold by the dealers, and there is a one red dot which is the trust mark dealer. So individual dealers, that is the blue dots. So it turns out that they have more number of kilometers driven, individual dealers. Okay, and we can see that there is a chunk which have like looks like majority of the chunk, maybe say 60% of the data, both be it individual or dealers, have kilometers driven less or equal to say 300,000 kilometers, and their selling price are ranging say from 200,000 to 400,000 cars. So these are those less expensive cars but heavily used, everyday use cars. And then did another exploratory design for kilometers driven versus the transmission type and versus their selling price. So we can see a clear bifurcation of automatic cars tend to be expensive compared to manual cars, and the kilometers driven for automatic cars are lesser than the kilometers driven for manual cars. That's what we can figure it out from this plot. And when we're plotting them, so Seaborn library, like in short, it is as SNS. When I'm running a scatter plot, so I need to pass the Y parameters and the X parameters. That means on my Y axis is my selling price, and on my X axis is my kilometer driven, and there is a hue parameter, that means a third parameter, which means I want to look in through transmission type. right? Setting in the X label, PLT, that is plotting the Y labels and the X labels, giving them a font size, font weight, setting up their the X limits and the Y limits, that setting up a scale basically, on what scale the Y limit should be, on what scale the X limit should be, and basis that how we are determining it, and finally a title to it. plt.show is just one code used to show or basically display the result. Now, next is most cars sold in the fuel type also. So we saw that already with it was petrol and diesel. Distribution of these numerical features. Now over here, this is an important and interesting part to see how they are distributed. So vehicles age, as we saw, that it is there is a little bit of skewness coming in. That means there are vehicles which have age greater than say 15 years, and we saw that initially in the data.describe. And here again, here with the help of the QQ plots, they're telling. So how do we interpret QQ plots? Is the dots, if they are farther than the red line, that means there is more skewness or the distribution is wider. Okay, so mileage over here, it is and it is fairly well distributed. Engine distribution, so you see there are a lot of variances out here. And same thing is being seen in the QQ plot as well. Max power, also there is skewness. Seats distribution, okay. Now seats distribution is not a continuous data set. It's more of where it is more of a categorical data set, or because there are certain fixed number of seats. So usually we have 5-seater cars, and that is why where we see this frequency highest, the distribution highest over here, from between 4 to 6, and tentatively that is 5, right? Or there is a 7-seater car. So there are 5 or 7-seater cars which are more in demand. Selling price, we already know that it is very much skewed. Okay. And observations again to just see that, yeah, the age, kilometer driven, engine, max power, selling price, they are right skewed. Distribution, mileage is close to a normal distribution, but there is a bit of right skewness present, and seat is a discrete feature. Also looking at the box plots around it, so I've just run a function for all the numerical features. So we can see that vehicle age has got certain number. Now these dots over here, they mean outliers. Okay, so vehicle age has got some bit of outliers. Kilometers driven is very skewed. Okay, so there are a lot of dots over here, or I could say, likewise, even in engine, there are outliers. Mileage has got mileage looks the one which is more well distributed. Max power, seat, we will not consider much over here, because again it's a discrete feature, so we don't want to use it. We will not be using a box plot to interpret that. And selling price, finally. Moving further to understanding the correlation, and this is again a heat map. To read this heat map, we say if on a positive note side, that is when it is closer to 1, then we say that it is positively correlated, and if it is closer to a -1, then we say two features are inversely correlated or negatively correlated to each other. So from this data set, we can say that max power and selling price, they are very much correlated, positively correlated. Max power and engine are positively correlated, and that is pretty intuitive, right? Thinking about that, yes, max power and engine, if there is a good engine, a heavier engine will definitely have more power. Okay. Pre-processing and feature engineering as the next step to an important step to running the ML flow. Here, what I've done is I'm removing the outliers in terms of capping the outliers using the IQR method or the interquartile range, where capping the top 25, the first quartile and the third quartile, the values um, lesser than the 25th percentile value, or the values greater than the 75th percentile value or the third quartile. I'm capping them to a limit, that is, I'm setting it to the upper limit or to the lower limit, right? And that is, the upper limit and the lower limit over here is being set by 1.5 times the IQR. Okay, and IQR is calculated just by taking the difference of the third quartile versus the first quartile value. Running this function to all the continuous features. And now if I run the same numerical distribution plot and the QQ plot, we can see that kilometers driven now, they look to be more well distributed and across. Likewise, for engine, for max power, we see that there is a well-formed, a better forming bell curved around. Moving on to the next part is to set up, to transform the categorical variables and to scale the numerical variables on the same scale. So we're using standard scalar, one hot encoder, and binary encoder. So brand and model are not really required over here. I'm dropping them because that information is already being captured by the car name. So here, then I'm splitting the data set from independent versus dependent features. That means my X features and the Y features. So Y will be only the selling price, and other all I'm putting them in my X label or X variable. Train test split, I'm doing it here. This set of code, and this is a standard code, which a format which has been followed with giving a test size of, say, I'm putting 20% of the data in my test, and the other 80% I'll be using it to train the model. And yeah, now just looking how the data set looks like. So after splitting the data into train and test, so there are 12,195 observations which go in the train set, and 3,049 observations goes in the test set. Now here, what I'm doing is I'm running up a function again to see my I'm basically evaluating the model. So what are the parameters that I've put in? Actual value, the predicted value, the X test value. So what this function usually does is that it takes the actual value, predicted value, and the X test value as an argument and returns the mean squared error, mean absolute error, root mean square error, R square, and at the adjusted R square, which is rounded to 3 decimal points. So these are again functions which we've called from the different packages, different libraries from scikit-learn. Okay, and now the next thing is I'm also creating up a dictionary of models, the 5 models that we'll be running through: linear regression model, elastic net regression, support vector, decision tree, and a random forest model. Creating another model function to run the different models. So in this, the parameters are, it takes the model object, the X-train data, the Y-train data, and the X-test data as its argument, and trains the model and gives the prediction for the train data and the prediction for the test data. So I'm putting them all in a function so that it is easier for me to run all these models at the same time, quicker, and not just set up individual codes. Then I'm creating empty lists to store all these outputs. That means the model names, R squares, adjusted R square values, MSC, MAE, and RMSC scores. Now, this big chunk over here is nothing but training all the models and getting their performance and storing it in an empty list. Model trainer running them, model evaluator running them, and then model evaluator running on the X test, and then appending these values as and when the model has been run. So when I'm running the linear regression model, so the model is performed on the training set, the mean error, this is such a huge error which I'm getting, mean absolute error, root mean square error, R square, and the adjusted R square. So these are the values for the training set and the test set. So the output is similar in a similar fashion for all the 5 models. So R squares, if you just look at the R square, so when we run a linear regression model, the R square score is 0.84 and 0.839 is the adjusted R square. For the train set, whereas for the test set it is 0.844 and adjusted R square is 0.842. What it means, the adjusted R square is basically it will penalize the model for any additional feature which is not giving any different information from the already existing features that the model was using. So an increase in the feature, and if there is no valuable information given, then the model is penalizing, and that is what the adjusted R square means over here. R square is nothing but how good the model is, how strong the model is basis the given features, and to what extent the X features are able to explain the prediction done for the Y or the target variable. Likewise, we're doing it for elastic net regression model, support vector regression model, decision tree regression model, and the random forest models. So I'm now finally what I've done is I am tabulating these model performances in a data frame, and these are the values that I'm giving. So how do we to interpret these models? To interpret these models, we will see that the random forest regressor is the one which is giving the maximum R square. That means using a random forest model, the R square, the strength of the model is highest, 0.933, and the adjusted R square is also pretty high over here. Whereas the RMSC score, or the root mean squared error, is very low. Now, why this is there? Because random forest models, they are doing a good job over here, whereas support vector regressor models, they have a negative R square. That means the data set, this support vector regressor is not a good algorithm to run on this kind of a data set, and it has got a very high RMSC value too. Okay, linear regression does a good job over here again, and the RMSE score is relatively more than the random forest regressor too. So if we have to choose the best model, then of course random forest takes the lead. Now here, the same activity using the yellow bricks package, what I'm doing over here is with the yellow bricks, we can look at the features, and again, visualizing these. What are those? After running the algorithm, we are visualizing that what are those important features which are actually helping build the sales price. So we can see that engine is a very important feature which is helping to predict the sales price, and then comes in mileage, which our mileage is mileage versus engine again. So basically, we can see that these are the five important features, but my engine is a very important feature for this data set. Okay, and then the next one is the kilometers driven also, because if you see here, then it is moving higher up. So the light orange yellow color over here is depicting that it is the next important feature. Uh, with yellow bricks, we can also look at joint plot visualizer. That means take two certain features, X features, and see how they are working on the Y feature, Y variable, I mean. So engine and mileage, how they're doing it on my price, the selling price. So here, yes, the combination of these two are again saying that there is a positive correlation. The strength of these two are also positive in predicting the price. Residual plots is one of those measures to see in linear regression that how good is my errors, how evenly distributed are my residuals or the errors in the model. So if there is a heterogeneity, or if there is a homogeneity in these residual plots, that means if there is a kind of a pattern which has been developed, that means the regression model is not a good one. And then there could be some more ways to run the plot, run the regression, and different models can be explored over here. But over here we can see that the dots for the train and the test, the errors or the residuals are pretty evenly distributed across this black line, right? And even if you just see that there, you can see a bell or a normally distributed curve. Cook's distance is one way to look into the outliers. Over here, the outlier detection. But as you know that initially we capped, we treated those outliers, we removed the outliers by capping those to the upper quartile, upper limit and the lower limit. And that is why the Cook's distance over here, we see that this red line over here doesn't show, it is somewhere near, and the red dotted line over here is also closer to 0. So that means there is no outliers in this data yet. And lastly, we look at ridge and lasso over here. So ridge selection to see if, because there were outliers and because there were a lot of features in the data. So if all these features, are they overlapping features, or they, each of these individual features have an individual information or a different or a unique set of information to provide, or to help in predicting the price. So with this rich information, I'm using using that rich score over here, the alpha score over here, what should be my alpha value over here. And with that score, I'm again running the setting my X test and train over here using this and looking at my prediction error. Turns out that yes, there is lesser error. Again, the R square is pretty good. So we can say that this is a good model. So the prediction error are evenly distributed, and you can see that the best fit line, the best fit line over here is pretty close to the identity line. Okay, so that's yeah. So that's about it, about this session. You can also explore more using this yellow bricks package over here. And I'll also be putting the link of this to look into more details and see how more things can be done in a regression model. Um, and if there are any other any new techniques to be looked up to, for example, over here, if we talk about, so they have also given examples about doing a feature extraction, and and doing more about learning more about what different models can do, different APIs. Um, so regression, yeah, you can go to regression visualizers, and there, these are the explanation and the different set of codes. You can take it and run it on the same data set or on a different data set of your choice. So yeah, that's it from my side. I hope this session was very valuable. um, you can post your questions, or you can also email me for more clarifications on this session. Thank you so much for listening to me and viewing this session. Thank you.